this week we are going to discuss Anova, the Anova test. The Anova test, which stands for analysis of variance test, is actually similar to the t-test that we talked about a couple of weeks ago, except where the t-test compares two groups of continuous variables, the Anova test can compare 3 or more groups. Now, the t-test and the Anova test, they're actually so similar. I'm going to use pretty much the same example that I used in the t-test chapter, except I'm going to add an additional group to it. So the data set will look very similar. So if you're feeling comfortable, if you are proficient with the t-test, if you feel comfortable that you can interpret a t-test, well then you're actually already more than halfway there to comprehending the Anova. So the only real difference between the t-test and the Anova test is really the ordering of the test run and interpreting the test results. And then there's several other minor differences that we'll talk about along the way. So, with that being said, let's go into, we're actually going to expand the example from the t-test chapter, in which we had group 1, we had 3 groups, and each group of students were getting taught by a different math method. So group 1 was math taught as usual. Group 2, Z math, and now we have a third group, which is group 3, and this group is going to be flashcards. And so the Anova test is going to reveal which, if any, of these groups statistically significantly outperform the others. So this is just a little bit of background on this example. So we have Dr. Zinn and Dr. Zorders, who arranged to offer Z Math their innovative method for teaching students the multiplication table to 4th graders. The principal is willing to try the Z Math method, but she is also curious about how effective multiplication flashcards with a math coach might be. So our research question for this particular study would be, which is the best method for teaching multiplication? The usual teaching method, Z-math, or flashcards with a math coach? So this is our groups. We have a total of 9 4th graders, and they would be randomly assigned into 3 different groups. We would have, so the principal randomly draws 30 names from the hat, and these students are assigned to, we have 30 who will be placed in the usual teaching group, and this is going to be our control group. Then we have 30 names randomly drawn, assigned to the Z-math group, and then the final 30 will be in the flashcard group. So, for the procedure for this particular study, from 10 o'clock to 11:30 every morning, the usual time for the daily math lesson, the students in the control group will go to room 14 where they will receive their regular math lesson. So, their regular lesson as usual. Students in the Z-math group will go to room 8 for their Z-math lesson, and then finally the students in the flashcard group will go to room 20, where each student will be paired with a community volunteer to work with the student using flashcards. So the students in the Z-math group, they are instructed not to disclose the Z-math method to other students, just as well as the flashcard group. No one is allowed to share any method with any of the other groups. So, after 4 weeks of our intervention, we have all students will be given a test where they will have 10 minutes to write out the entire multiplication table with the solutions on a blank sheet of paper. Now, our hypotheses for an Anova test is a little bit different. So notice we have more comparisons to make. We have 3 groups now, so since we have more groups, more comparisons to make, which will result into more hypotheses. So Our null hypothesis, remember that there's no effect at all, so I would say there is no statistically significant differences in the test scores among the three groups. Now, our next four hypotheses, we're actually going to compare each group to one another. So, first, our first alternative hypothesis, H1, the Z-Math group outperforms the Math as Usual group. The flashcards group outperforms the Math as Usual group. The Z-Math group outperforms the flashcards group. And finally, the flashcards outperform the Z-Math group. So, as there are more groups, there are more comparisons to analyze, which is what Anova is all about. So, for this example here, we are actually going to use the SPSS file called Anova example, found in your learning module. We're going to go ahead and open this up, and we'll look at that data set.
This is the data set here. We have two variables. We have group and score. And so notice, let's see, we have a total of 90 participants in this study. And notice our group is either labeled 1, 2, or 3. So we actually have, so records 1 through 30 is going to be for group 1, and this group is going to be Math as Usual group. Then we have 31 through 60, which is going to be group 2, our Z-Math group, and then finally we have 61 through 90, which is our new group, and this is the data for our group 3 flashcards group.
So our assumptions for an Anova test, we have 3 assumptions, and I actually forgot to add one. I'm going to go ahead and add one right here. I'm going to say, so the first thing I'm going to talk about is the sample size. So basically, you can actually run an Anova test with an N of any size in the group. However, when your N is at least 30, the Anova is considered more robust. So we're going to say N can be any size, but when the N is at least 30, the Anova is considered more robust. So that is an assumption, our first assumption, and this can actually, we can actually figure out the size of our sample when we run our Anova test, and we can look at the descriptives. The next criteria is normality. And so we can check for normality by inspecting the histograms for our data set. So let's look at our data set here. So we want to create a histogram for the scores in each group. So first, we can click on this little icon here that stands for Select Cases. And let's click on if condition is satisfied, and we're going to put group equals 1. So we only want to look at our first group here, and notice what happens. Let's see, so we're filtering it by group 1, and let's go back to this data set here. So notice group 1 here, and notice what happens to group 2 and 3. Groups 2 and 3 are marked out because we only want a histogram for the scores in group 1. And it shows here, it actually shows a column that our group is filtered by group 1. So now we can go to Analyze Descriptive Statistics, and we can go to Frequencies. I want to remember histogram, you can only create histograms on continuous variables, and our continuous variable here is scores. So we're going to move scores over, click on charts. I want a histogram, and I want to show the normal curve on the histogram. And this shows our normal curve. Okay, it's roughly normal, so I think group 1 is okay. And now we're going to do the same thing with our other groups. So I can select cases again. I want to focus on group 2 this time. Go to frequencies, score, okay. This is my second histogram, looks okay as well. And now our final, let's go to select cases again. So notice whenever we select group 2, group 1 was marked out as well as group 3. So let's go to select cases again. Now I only want group 3. Click OK. It's telling me that it's filtering by group 3. So now I can run my analysis again. Go to frequencies, scores already in there. And we have our histogram roughly normal. So normality is our assumption of normality has been met for all 3 of our groups. So now we will check on our sample size. Normality has been met. Now let's look at homogeneity of variance. So this is actually going to be checked whenever we run our Levene's test. The homogeneity of variance will be checked, and it will be looked. We can find that out in our results section in our output. But basically, so the rule of thumb here is none of the groups should have a variance, meaning that standard deviation square, that is more than twice the variance of any other group. So for instance, if I had group 1 and the variance is 20.1, group 2's variance is 24.7, group 3's variance is 90.6. Now notice 90.6 is more than twice the variance of group 1 and more than twice the variance of group 3. So this test, this homogeneity of variance test, would fail, since 90.6 is clearly more than twice as large as 20.1 or 24.7. Now, when we look at this in the results section in our output, we're basically looking to see if that significance test, right? So that Levene's test, if we want our variances to be the same, we want them to be non-significant. Okay, so this example right here, this would actually give you a significant test. It would give you a significant p-value it would be more, this would give you a p-value of less than 0.05 for this particular example. What we want our p-value to be more than 0.05. We want our variances to be the same. We do not want them to be significantly different. So if variances are the same, we will meet the Anova assumption. So let's run an Anova test. Going back to our data set here. Now, before we run our Anova test, we want to select all cases again. We don't want to filter out any cases. And we can check this because it says filter off. We're using all of our data. So in order to run an Anova test, go to Analyze. We want to compare means, one-way Anova. And we want to move the continuous variable, which is analyze here. We want to move it to the dependent list. And we're going to move the variable that contains the categorical variable, which is group. Group is our categorical variable here. This is going to move into the factor window. Now, if we would stop right here, oh, I'm sorry, let's do one more thing. Let's select descriptives, homogeneity of variance test, and the means plot, and we'll click continue. Now, if we stop right here and click OK, this is giving us our descriptives, this gives us our Levene's test, and this right here between groups, this is telling us a significance, our Anova test here, it's a significance, a p-value of 0.029. Now this is telling us that our groups are significant. There are significant differences between groups. But how do we know this isn't enough information to tell us which specific groups are different? Remember our hypotheses that we created, all of our alternative hypotheses? Each one stated a comparison between one another. So we need to actually take it one step further to do those multiple comparisons. We have to actually run our post hoc tests in order to do that. So let's go back. Let's go through our steps again real quickly. So we would go to Analyze, Compare Means, one-way Anova. Score is our dependent variable. Group would be factor. For options, we chose descriptive, homogeneity of variance, mean plots, and now we want to click on post hoc test. So we actually have two choices that I'm going to focus on. There's many options, but for our purposes, you would choose Tukey, the Tukey post hoc test, if all groups have the same N. So for instance, if each group had a sample size of 30, had 30 participants in each group, or you can choose the SIDEC post hoc test if the groups have different N's. So for instance, maybe group 1 had 40, group 2 had 55, and group 3 had 36. So if you don't know the N for each group in advance, you can select either Tukey or SIDEC, and then you would check the N in the resulting report. So if you guessed wrong, if you thought, oh, I think my groups are the same, I'll choose Tukey. I ran my report, I looked in the descriptive section and realized, oh gosh, my N's are very different from one another. Just rerun then you would just rerun the analysis using the appropriate post hoc test. For our purpose, we know that we have 90 participants and each group has an N of 30, so we'll use Tukey for our purposes. So let's go back to our Anova test. We're going to click on the Tukey Anova, the Tukey post hoc test. and now we will click OK. So we have our descriptives. We can check our homogeneity of variances assumption. It's greater than 0.05. This tells us that the variances among the groups are not significant, meaning that our variances are the same, which is good. That's what we want. So we do meet the assumption. Our homogeneity of variances assumption is met. Again, this is saying that we have significance among the groups. And now here are our multiple comparisons. This is what we are very interested in here. So this, think of this kind of like, it's almost set up like the multiplication tables whenever we were growing up. And so think of it as you would see two 32s in the table because 4 times 8 equals 32 and 8 times 4 equals 32. It's the same thing here. So for instance, we have 0.045 as the significance value. We have 0.045 because of the table. The way the table is created, it's getting compared twice. And so we have math as usual versus Z math would be a significance value of 0.045, and then just vice versa, Z math and math as usual 0.045. So don't let that confuse you. Now remember, with our hypotheses, we were making 3 comparisons, sorry. So our first comparison is math as usual and the Z math. So this has it's actually comparing the mean scores here. Remember, we can find all of our mean scores here. 0.7, our mean of math as usual, 75.77, Z math 80.97, and flashcards 80.63. So what our Anova test is doing, it's actually comparing those 3 means to see if their means are significantly different. So our first comparison, math as usual versus Z math, we have a p-value of 0.045. And so since the p-value is less than 0.05, this is telling us that for score, this is telling us that there's a significant difference between math as usual and the Z math test, the Z math method. The second comparison is between math as usual and flashcards. Math as usual and flashcards. And this produces a significant value of 0.066. So since this is greater than 0.05, this tells us that there is no significant difference between math as usual and flashcards. And finally, our third comparison is going to be between Z math and flashcards. This gives us a significance value of 0.987. So again, no significant difference between Z math and flashcards. So this concludes our comparisons. So let's look and see how we would write up these results. So the results of Anova for score, it's much easier if those 3 comparisons that we were talking about, it's much easier to interpret if you place them in a table. So that's what I did here. This little symbol, this is a symbol for mean. So basically all I did, I put each group math as usual. I put the mean from that descriptives table. So math as usual mean versus the Z math mean. These are the 2 means here. This shows a p-value of 0.05. We have math as usual versus flashcards, p-value, and ZMath versus flashcards, this is the p-value here. And I indicated with an asterisk where it was significantly different at a p-value of 0.05. So when writing my abstract, I can say a group of 94th graders was randomly assigned to one of 3 groups to determine which method of teaching the multiplication table is most effective: math as usual, ZMath, or flashcards with a volunteer math coach. After 1 month, students in the ZMath group learned an average of 80.97% of the multiplication table, significantly outperforming students in the math as usual group. Those who received a math as usual learned an average of 75.77% of the multiplication table, and those who used flashcards learned an average of 80.63%. So this states the means for each group as well as the groups that were significantly different. So again, explaining again how, just giving you an illustration of how the more groups you have, it's also going to increase the Anova post hoc multiple comparisons. So t-test, if you have 2 groups, we only have 1 comparison, group 1 and group 2. However, with 3 groups, like what we just looked at, we would actually have 3 comparisons: group 1 and 2, group 2 and 3, and then group 1 and 3. 4 groups, we would have 6 comparisons, and so on and so forth. So again, the number of multiple comparisons increases substantially. So I hope you have a better understanding of the Anova test, how to run the Anova test, how to interpret it. So good luck with your assignment this week, and feel free to join me in Google Hangouts if you have any questions. Thank you.